Okay, good afternoon, pilot teachers, and good afternoon, students. Thank you. Sit down. Note, from our previous lesson, we looked at plate boundaries in Papua New Guinea. We studied about plate movements, and we said that generally tectonic plates would actually do three movements: the movement of converging, diverging, and those plates that slide past each other. As a result of those movements, there are plate boundaries are also considered, or they can be classified as a destructive plate boundary, whereby two plates converge. You can have a I'll rephrase that. A constructive plate boundary where two plates diverge, they move away from each other. You can have a destructive plate boundary where two plates converge or move towards each other. And we can also have what we call passive or conservative plate boundaries where plates slide past each other. We've looked at a lot of information surrounding converging of plates, and we've also looked at different types of plates that converges: oceanic plate with another oceanic plate, continental plate with another continental plate, oceanic plate meeting up with a continental plate. And as well as that, we also looked at, in our last lesson, the plate boundaries in Papua New Guinea. If we can recap very quickly on the readings and the information which I ask you to look at on the plate boundaries surrounding Papua New Guinea. Papua New Guinea actually does not sit right at the edge of the Pacific plate and the Indo-Australian plate. Rather, there are also different little plate boundaries within the country itself, and that is what we looked at in our last lesson. So if we looked at some of the main points from the information on plate boundaries in Papua New Guinea, some of the features that are found within this area here, Papua New Guinea, first of all, the New Britain Trench. We found out that that is as a result of the Solomon Sea Plate colliding with the South Bismarck Plate, resulting then in the subduction of the Solomon Plate, giving us the New Britain Trench. We also had the Woodlak Basin, of which we noted that that is an area of low seismic activity, the Woodlak Basin around the Milne Bay waters. We also looked at volcanic arcs in Papua New Guinea, and one of those from the New Britain Islands all the way to the Long Island. And those were formed as a result, again, of the converging of plates, resulting in the subduction, and where the oceanic plate is, volcanic arcs are actually created. We also looked at volcanoes which are found within Papua New Guinea. Generally, we did not specifically look at those main volcanoes in the country because of the fact that that topic, especially on volcanicity, that will be the next topic that we will be moving on to, and we will look at identifying the main volcanoes in Papua New Guinea when we come to that topic. But in Papua New Guinea also, we note there are a lot of volcanoes, and those volcanoes can also mark the little plate boundaries that we have in the country. Note also along the Bismarck Sea, we note the movement of the South Bismarck Plate towards the east and the North Bismarck Plate towards the west. And along that area, there is a zone of shallow earthquake which is found within that area or the boundary. And from studies, it has shown that there is a left lateral strike-slip fault which is actually found around that area where the boundary of the North Bismarck Plate meets the South Bismarck Plate. And the movement of those plates in that area is actually sliding past each other. One plate moving to the east, the other one moving to the west. Today we will go on now to looking at information on transform fault. And for information on transform fault, we are going to look at a case study. And the case study is going to be based on the St. Andreas fault. And that case study will maybe be able to enable or help us understand a little bit more on the plate movement of one plate sliding past each other or moving past each other. We've looked at already converging of plates, and now we are moving on to the next movement, and that is when plates slide past each other. And a case study that we'll concentrate on will be that of the St. Andreas fault. So you should have information on the worksheet there, of which that is going to be your background readings that you're going to go through for answering or completing the activities which I will assign on that particular movement. Before we go on to looking at those activities, let's recap and revise also on what we've covered on plate movements of plates sliding past each other. Note from the information on the monitor, when two plates slide past each other, what is usually formed there is a transform fault. And the movement, you can see here as shown, one plate moving up, the other one down, or you can have a plate moving across, the other one moving across in the case of the North Bismarck plate and the South Bismarck plate in Papua New Guinea. The boundary where the plates actually meet in terms of one plate sliding past each other, sorry, not one plate, two plates sliding past each other, that boundary where the plates actually slide past each other is referred to as a passive or conservative plate boundary. A classic example with regards to passive plate boundary would be that of the North American plate and the Pacific plate. As a result of that, a feature which is created as a result of that movement then is that of the St. Andreas Fault. So if we look at the map of North America here, you can see the North American plate moving in this direction, and you can see the South Pacific moving in that direction. As a result, what is created there is a fault line, and that fault line then is referred to as the St. Andreas Fault. A second diagram here showing us the same thing, this time of the North American continent. We can see the North American plate moving towards the south and the Pacific plate moving towards the north. The green line here represents that fault line which is created as a result of the moving of the plates past each other. Okay, we have a photograph. I think we've seen this photograph already from our previous lesson, but here is a good indication to also tell us that definitely plates are actually sliding past each other. You can tell by looking at the course of a river stream here, and you note once upon a time this particular stream or the bed here connects, they join up together. But what has happened now as a result of that movement, this particular stream here has moved slightly in this direction, and this particular stream, the course now has been deflected, moving towards the direction. So if you can see an evidence to state that the plates are actually moving is by looking at the streams that cross that particular fault, the St. Andreas Fault that is. So if you look at this stream here, you can see the displacement. It's supposed to connect with this one here. So by looking at this information, you can say that this plate here is moving to that direction while this one here is moving to that direction. So the river courses deflected as a result of that particular fault. And the fault line, the St. Andreas Fault, is supposed to be here. Not very visible from our monitor, but we can work out, as shown by the arrow here, it's supposed to run in that direction. Okay, another photograph still showing us the same information. Stream channel, which is displaced by the St. Andreas Fault. The arrows now on either side of the fault indicate the relative motion or movement of the plate. I think this is a little bit more clearer because you can really see the fault as shown there. And some information there to help us maybe understand a little bit about that movement in relation to some of the famous locations. We'll take, for example, we are maybe familiar with the city of San Francisco, that is. And we are also familiar with Los Angeles. If we want to really note the movement of those plates, we can look at the location of those two cities. And from our readings and information, it might be able to help us see in which direction or the change in the location of those cities in relation to each other as a result of the motion or the movement of the plate. So for this particular country here we're looking at, the red line here indicates the famous St. Andreas Fault. You look at where it extends. It extends from this area all the way towards the mainland of Mexico. So that fault line, along that fault line, you will note towards the Pacific Ocean is the Pacific plate, and the direction in which that is moving is towards the north. And On the west, sorry, not on the west, on the east is the North American plate, and it is moving towards the south. When we look at the information from the readings, bear in mind the location of those two cities, especially Los Angeles, if we are talking about plate motion and the rate at which this particular plate is going to move. And keep in mind where this particular city might be located, maybe in the next 25 million years, and etc. And if we can note the movement to which direction or where it will be located in the next perhaps 25 million years, then we can tell about the motion or the movement of those two plates in relation to each other. I'd like us now to move over to the worksheet or the handout, and the information where it states the heading in greater depth, that's what I'd like us to look at, and then the rest of the information you will be discussing in pairs to complete a couple of questions which I will put up on the board and also from the monitor. So if you can make reference now to the reading titled In Greater Depth, California's Greatest Fault, the St. Andreas. We all have that information? Okay. It tells us there that the St. Andreas Fault in California is the best known geologic structure in the United States, but the geologists and seismologists who study it admit that our knowledge of its activity and its history is far from complete. Actually, the St. Andreas Fault is the longest of several sub-parallel faults that transect Western California. So if we look at the information from our worksheet and perhaps also from the monitor, the St. Andreas Fault, this is only one fault line, but there are also many other faults within this region here as a result of the plate movement, the passive plate boundary that is, and the plate movements whereby the Pacific plate is sliding past the North American plate. Collectively, these right lateral faults are known as the St. Andreas Fault System. So together, all of those little faults which are found in this area, together with the main St. Andreas Fault, would make up the St. Andreas Fault System. It tells us there, the system, so that whole area we're looking at now, is a belt approximately 100 kilometers wide. If you look at the map that you have in front of you, you will note that there is an area that is shaded a little bit darker from your map. Perhaps you can turn to the next page and the map on the next page, similar information, but it is a little bit more clearer. That's the map showing us figure 15.3. You make reference to that, 15.3. Double check. Okay, if you look at that map, 15.3, you would have noted that there is an area which is shaded a little bit darker, and that is showing us at least the width of this particular belt, about 100 kilometers wide. So we're looking at the thickness of that sub-parallel system, or the parallel fault system here, of a width of about 100 kilometers wide. And the fault line itself, or the Andreas Fault System, extends to about 1,300 kilometers long, and it extends into Mexico, ending at the Gulf of California. So the length of the system is about 1,300 kilometers long, and the width of it is about 100 kilometers wide. And that's not only looking at the St. Andreas Fault alone. We are looking at generally all the different faults also within this system. Okay, it goes on to tell us that Los Angeles is slowly moving towards San Francisco. So if we can make reference now to our map, Los Angeles is here, San Francisco is here. So here it is telling us that Los Angeles is slowly moving towards San Francisco. See the fault line. It runs here. And it tells us that at an average rate, the movement is at an average rate of about 2 centimeters per year. You can check 2 centimeters from your ruler and see how big that movement is per year. It also goes on to tell us that Los Angeles could be a western suburb of San Francisco, or San Francisco, an eastern suburb of Los Angeles, in some 25 million years from today. So if the motion is at 2 centimeters per year, 20 million, 25 perhaps million years from today, this particular area here would be a western suburb of the San Francisco city itself. Or San Francisco would be an eastern suburb of Los Angeles if it is moving at a rate of 2 centimeters per year. And in 25 million years from today, that could be possible. Geological time scale we are looking at, 25 million years from today. None of us would actually be here to maybe note that. But studies have proven that it might happen that way. Earthquakes are actually produced by sudden movements within the fault system. The St. Andreas Fault is actually not a simple crack, but a belt of broken and ground up rock, usually 100 meters or more wide. Its presence is easy to determine throughout most of its length. Along the fault trace are long, straight valleys formed by erosion and subsidence that show quite different terrain on either side of that particular fault. Along the fault trace are long, straight valleys that show quite different terrain on either side. And stream channels, they follow much of the fault zone because the weak ground-up material along the fault is easily eroded. Locally, elongate lakes, which are known as sag ponds, are found where the ground-up material has settled more than the surface of adjacent parts of the fault zone. The fault itself, the St. Andreas Fault that is, was named after one of these ponds. And from your worksheets or handout, you will find that St. Andreas Lake that we are talking about just south of the San Francisco city. So if you can make reference to the worksheets, you will find also a photograph which is showing the St. Andreas Lake, of which the fault line was actually named after that particular lake. The rest of the readings and information you can make reference to when you do your discussions. Okay, looking at some of the factual information that we have from different sources, note, the information is presented also from your worksheet, but if you look at this diagram has actually been turned so that we can fit that information on the monitor. It is supposed to be standing from the top down, but we've put it sideways, so note, the red line here represents the St. Andreas Fault. If you look at what we have read on the width of the system, the orange color area here now represents about 100 kilometers wider. We're looking at the system, and 1,300 kilometers long in terms of the length of the whole system. Within that system comes in the famous St. Andreas Fault, which is just one of the fault lines that is found within that system. Okay, we still have the same information again, but this time note that this is supposed to be the two major breaks on the St. Andreas Fault in California. Each of the break, this is one break here, there's another break here. Each of the break occurred during a giant earthquake. And each old break is now a seismic gap and the future site for another, perhaps giant earthquake. Note there, it tells us that one of those breaks was formed as a result of the 1906 earthquake, and the other break as a result of the 1857 earthquake, of which those two are some of the major earthquakes that shook this part of the world as a result of the movement of the plate or of the plates in that region. Okay, we come now to the information you have, the worksheet that is, and you're going to do some discussion. I briefly went through the information on the famous St. Andreas Fault. Most of the information is presented from these worksheets that are given, but you're not going to read individually, because if you read through individually, you're not going to have time to actually complete the discussion. You're going to skim through. And from the skimming, you're going to see if you can pick up the answers to the the two activities I'd like you to do. The first one, discuss in pairs or discuss in threes. And then explain the general plate motion along the St. Andreas Fault. This should be easy. After your discussion, you just make note. What is the general motion along the St. Andreas Fault? You're not just going to say one going that way, one going that way, but a little bit more information around the plate motion and maybe the features that can be actually located along the fault line. Then the second activity that I'd like you to do again in pairs, identify possible location of Los Angeles 25 million years from today if the average rate of movement along the St. Andreas Fault is about 2 centimeters per year. So using the maps that you have, just locate, maybe by putting arrows to indicate where you think Los Angeles would be 25 million years from today if the motion is at 2 centimeters per year. So those two activities I'd like you to work around. And while you're doing your discussion, maybe some of you would like to help each other understand a little bit more about this particular plate, not plate boundary, but this particular feature, the St. Andreas Fault that is. And if you have any questions while you are discussing, feel free to ask. I'll give you at least maybe say 10 minutes, and then we'll look at general answers to those for the conclusion of our lesson. Explain to me how you distribute that. Okay. So where is you given him 35? Okay, put 35 there, sorry. Again, while you're discussing the information, if there are any queries or questions you have with regards to this particular case study we're looking at, you feel free to ask. No, you will not be able to just get what is actually given for us here is calculations that have been done by geologists, seismologists, those people who have used different methods in identifying and working out. Maybe later on when you read, you will find that one of the things they looked at perhaps was the rate and earthquakes. Maybe perhaps they looked at the major earthquake from the other one, and they looked at how many years it took for those major earthquakes, and they looked at the magnitude of the earthquake itself, and then they were able to work out by how far the movement along the fault line. But they've got their own way of calculating, of which I will not go into detail on, but I think it's explained somewhere in the readings if you do read through, yes. So there is no scale. I thought I was going to relax and come back.
There's the picture that you showed about the scenarios, that you showed the river flowing down and now it's clear. How do we know that both plates were moving? I mean, what do you say only one plate was moving and it kept moving?
Possible, yes. You could actually look at the shifting of the maybe the certain locations. So we take San Francisco, we take Los Angeles. You could say one plate was static, it was there, and the other plate is simply sliding past it, or
One
the
plate
two.
was static.
You could say that, but from the information here, it's been telling us that one plate is moving that way, the other plate is moving down. So here we are saying that the two plates are actually sliding past each other. But in that particular movement, you can also have, like say for example, if we're looking at this here, you can say this plate here perhaps can be static while this plate is actually moving past it, and that is still possible.
Um,
Because if you look at San Francisco, if they are moving, we are saying that maybe Los Angeles somehow would be here, and if it's going to be moving here, that means that this plate here is actually, yes, or it's moving at a very slow rate compared to this one coming at the top.
So let's say it probably moves up every other.
Yeah.
The sun's already up.
Exactly. Or if they are both moving, then what could happen is that these two here, because this is on the other side, this particular, if you look at San Francisco, it's on this plate here. Los Angeles is on this plate here. So they could actually meet somewhere.
So this is called sliding plate. Is there a name for when there's only one plate moving in one state?
We usually just call it transform fault passage because the passage or the boundary, because of the fact that the plate is sliding past the other plate, you would still consider it a passive plate boundary. Yes. And what is created there usually would be a fault, like in that case. Yeah. Good point to actually make, because really in reality, if we say that this plate is actually static, then this one would be here up there. That means this plate is actually moving, while this one is maybe very slowly. Otherwise, both of them would meet somewhere in the middle here, of which the description given will still be correct. This is to the east, is it?
Yeah.
East. And this one will be to the, no, this is to the east, and this one here will be to the west, where they meet. So they were saying Los Angeles could be a western suburb of the San Francisco, but whether they meet here or they meet there, we're not sure. But as far as we know, this is actually sliding or moving up. But it doesn't tell us about this moving down. So just check the information. Somewhere along that information, you might have. Sorry, about question one. Are you just discussing the general plate motion along the St. Andreas Fault? So there's the St. Andreas Fault. How do you think the plates are moving in relation to each other? So how do you think the plates are moving? First of all, you identify which two plates are you making reference to here. And then, to which direction are they moving? That's all. So in relation to each other, how are the plates moving? that's a good diagram that will help you with this. Shall we look at the answers to those two questions? And then for your homework, you're going to actually just read through the information from the worksheet or the handout, and then if you have any other questions with regards to the information presented on the background readings, you come back and we'll go through those questions in our next lesson. Okay, we look at those two questions, and I think we need to make reference to the diagram so that will help us with the answering of the two questions. First of all, the first question wanted us to look at the general motion or movement of plates in relation to each other with the formation of the St. Andreas Fault. Okay, Gibes is going to tell us, for the first question, just the general motion of the plates resulting in the formation of the St. Andreas Fault. Should I go back to the question? Okay. Gibes to explain the general plate motion along the St. Andreas Fault. Gibes is thinking very hard. Kathy, you're going to help Gibes. Question number 1. Explain the general motion of plates along the St. Andreas Fault. It's a simple question.
The two plates are sliding past each other. The North American plate is sliding south, and the Pacific plate is sliding north.
Okay, that's it. We're looking at a passive movement, a passive plate boundary, North American plate moving towards the south, the Pacific plate moving towards the north, resulting in the formation of the transform fault, of which that gives us the St. Andreas Fault. That's all you had to get down for first question. You didn't have to think hard about all the technicalities of it. Okay, then we look at the next question. Again, the next question is we're looking at just identifying, possibly, if we are looking at the two plates sliding past each other, and we're looking at information already from what we have read, we found out that possibly Los Angeles, 25 million years from today, might be a western suburb of San Francisco. So if we're looking at the average rate of movement along the St. Andreas Fault of about 2 centimeters per year, we're going to make an assumption of where we think Los Angeles might be in 25 million years from today. So maybe using an arrow, you can indicate that perhaps if we are saying that this plate is moving up that way and that plate is moving this way, you note the location of San Francisco. It's on the North American plate, whereas Los Angeles is sitting on still on the North American plate, but there is a plate boundary that is separating, or there is a fault line that is separating this particular section of North America from this section. So here, because of that fault line, this particular section of North America here is actually moving towards the north, and this section of North America is moving towards the south. So perhaps if at a rate of 2 centimeters, you might have an arrow pointing to the movement somewhere here. If we are saying this plate is moving to the south, this plate is moving to the north, perhaps they might meet somewhere along the line here. Again, we need to know the rate at which this plate is moving, and we need to know the rate at which this plate is moving, so we can locate where along maybe the fault line these two plates will meet 25 million years from today. But we are working on an assumption that generally this plate or this particular Los Angeles here might be somewhere towards this direction 25 million years from today. You with me? Okay, good. And that's the general assumption that we can make then. For your homework, I'd like you to go through the worksheet, and I will collect all the worksheets back tomorrow. So you go through and you read through for your homework. That will also bring us to the end of our lesson. Don't forget we have our test tomorrow. Okay, class, if you can now stand up. To the pilot teachers, our keyword for lesson 30 is Saint Andreas. Good afternoon, and thank you, students.